All right, so here is a question for you. You're holding a rifle pointed parallel to the earth. You drop a bullet and you fire the rifle at the same time. Which bullet hits the ground first? Ignore air resistance and ignore the curvature of the earth. So we're assuming flat earth. Okay, so pause your video and figure it out. All right, this is the same demonstration that I didn't do, right, that I described. Agree? So after the collision, gravity acts equally on both objects. And so it's going to be the same time, right? It's exactly the same time. Okay, so this is just review. The horizontal motion, vertical motion are independent. Those are the two-dimensional kinematics. You know, if we didn't have projectile, if we just had any old two-dimensional kinematics, we'd have that, right? And for projectile motion, we got rid of this one, we got rid of this one, and we put a minus g everywhere we had an a sub y. So that's it, you know. And this fabulous diagram, which is so important. Okay, let's see, what is that? 5. Before we do that, don't look at that yet. I want to do another derivation. And you're going to have to do these things in lab. And so whenever you're told to, prove that something equals something, you have to show every single step, right? You have to start off with a kinematic equation and do your math and come up with the answer. So this is just an example, all right? So actually, if you pay attention, what I'm going to do now, you'll have to do in a future lab, okay? So, I described this demonstration. We had the projectile launcher, right, with a little thing on it. And so the ball came out, and this ball went over here, and the ball that was in here just dropped to the ground, right? And I said that the times were the same. And if we were in McKay 132, with a tile floor, you could actually hear them hit this at the same time. So I want to prove it, okay? I want to prove it. Now, this is a kind of a special situation because when the ball was shot out of the projectile launcher, I had this projectile launcher perfectly set to be horizontal, okay? So in other words, the initial velocity in the y direction was 0. That's crucial, all right? I didn't have it aimed like this or like this. I had it aimed perfectly horizontal, all right? Now, you'll see in lab the time that the ball spends in the air, and we've got to give it a name, So it's time of flight, right? Time of flight, time in the air, okay? So what we want to prove this. We want to prove that the time of flight. We want to prove that the time of flight doesn't depend on initial speed, on initial horizontal speed, right? Because that's what we did. Remember, we did it slow, medium, fast, right? And the times were exactly the same. So we want to prove it. The time of flight doesn't depend on the initial horizontal speed. Okay, so how do you do it? You always got to start with something that's true, right? And that's usually a kinematic equation, All right, so okay, so let's see. So here we go. So we're going to use this one because it's a good one. All right, it has initials. Well, you'll see. All right, so here we go. So y final equals y initial plus v initial y delta t minus 1/2 g delta t squared. Great. Now we want to be a little bit lazy, so let's subtract the minus. Let's do that. This just makes it easier, you'll see. So final minus initial is delta. So now we have delta y, right? It just keeps it easier. Now, what's v initial y? Remember, it was perfectly horizontal, so it's 0. So goodbye, right? Okay. So now I just have delta y equals minus 1/2 g delta t squared, right? We're trying to prove that the time doesn't depend on the speed, the horizontal speed. Okay? So let's just solve for delta t, okay? So we have minus 2 delta y over g square root. That equals delta t, right? Okay, so look at that. So does the time depend on the initial speed? No, it does not. Why do you know? Because there's no initial speed in this equation, right? The time of flight only depends on the height, right, the delta y, and gravity, g, you know. If we would have had a v0, x in here, then we would say that the time does depend on the initial horizontal speed. But there's no horizontal speed in this equation, so we just proved it. Okay, so that's what you're going to have to do in lab, right? Something like that, right? That's called a proof, you know. All right. Okay, a person standing at the edge of a cliff throws one ball straight down and another ball straight up. Same initial speeds, all right? Same initial speeds. Neglecting air resistance, the ball to hit the ground below the cliff with a greater speed, right? So this one's just going to hit the ground, right? This one's going to go up here, then it's going to come down, right? So what's true about the speed of the balls when they hit the bottom? So while I'm erasing, you pause your video and figure it out. Okay, what's the answer? Why is that? Well, what did you learn some time ago? So let's say that's V0 up, that's V0 down, right? Well, what's going to be true? Look at just this one. This is going to go up, it's going to stop, and it's going to go down. So I'll just draw it over here. So what's going to be true about the speed here and the speed here? What did we learn about that? Remember we talked about symmetries a while ago? The same, right? So this speed here is the same as this speed here. So really, so this is V0. But this one here was shot down with V0 as well, right? So what's going to be true about the speeds when they hit the ground? The same. Now, obviously, this one's going to be in the air, longer than this one. But the point is that this one was shot down with V0. This one, when it gets here, the speed is also V0. So they're going to have the exact same speeds there. All right? So that's kind of cool. Okay, a battleship simultaneously fires 2 shells at enemy ships. If the shells follow parabolic trajectories, which they have to, right? Because we're ignoring air resistance and all that. Which ship gets hit first? All right, so there you go. So pause your video and figure it out. All right. What did we learn? That was I think it was chapter 2. We learned that the time up equals the time down, right? So that means that the time in the air is just twice the time up, or twice the time down. Agree? Okay. So which one is in the air the longer time? This one, right? Because this one, remember, the time only depends on the height, right? I mean, the delta y. So this one is in the air longer than this one, right? Because this time is longer than this time. So which one gets hit first? Which one gets hit first? B, okay? So I don't care about this is really wide, this is not so wide. The only thing that's important, remember, this time is just free fall, right? It's just free fall. So if you just stood here and dropped something, it would take a certain amount of time to reach the bottom, C here. If here you just drop something, you know, so which one is going to be longer? That's going to be short. This is going to be long, right? That's the only thing that's important, the delta y, okay, the delta y. So this is going to be hit before that one. All right. Now, this is a most awesome question. If you understand this one, you have a firm grasp of projectile motion. On the other hand, if you don't, you need to study some more. All right? I mean, that's all it's the truth. Okay. A physics student on planet Exodor, whatever that is, throws a ball that follows a parabolic trajectory. The ball's position is shown at 1 second intervals until t equals 3. At time equals 1, that's the velocity, right? All right, so we're supposed to figure out the velocity at 0, 2, and 3. And then we're supposed to figure out the value of g. Okay, so this is projectile motion, right? It's not the Earth. It's somewhere else, but who cares? It's still projectile motion. So everything you learned about projectile motion, you use on this one. All right, so this might take you 5-10 minutes. I don't care, but you've got to go through that thinking process. So please pause your videos and figure it out. Okay, so let's go through it. All right, so we only have 0, 1, 2, 3. So 0, 1, 2, 3. Now, we're given at 1 second, what's the x component? It's 2 meters per second. And also the y component is 2 meters per second, right? At time equals 1, x component, y component. All right, now look at, this is projectile motion. So that means that ax is 0, right? So therefore, what's true about the vx's? They don't change. So that means 2, 2, 2, okay? You have to be able to figure that out, all right? Just remember ax is 0, so the velocities in the x direction never change. Now, let's see. What is the y velocity right here? Well, it's 0, right? I mean, agree? It doesn't go up any higher. So, and we know that, right? You throw something up at the top, the y velocity is 0. So that means at 2 seconds, the y velocity is 0. Okay, we're basically done, all right? Because what do we know now? Well, let's look right here, you know. So a sub y, what's the definition of a sub y? It's, you know, it's the change in velocity over the change in time. Well, here we have some numbers, right? Here we have some numbers. So, agree? So it's going to be, let's do this minus this. Okay, so we're just looking at that, right? So this is our time final. This is our time initial. This is our velocity final. This is velocity initial. So it's going to be 0 meters per second minus 2 meters per second. And what's our delta time? Just 1 second. 1 second. So that's minus 2 meters per second divided by a second, which is minus 2 meters per second squared. All right? That's our a sub y. Okay? And again, come on, don't forget the basics. So a sub y is delta Vy over delta t, right? I mean, right? And so we just figured it out that it's minus 2 meters per second squared, but we can write that as minus 2 meters per second. So that means that the velocity changes by minus 2 meters per second every second. Okay? All right, so what does it have to be here? Remember, here it's 2 meters per second. So what does it have to be here? 4, right? 4, 2, 0, and then what? Minus 2, right? So it's 4, 2, 0, minus 2. Okay? That's all, right? Because look at it, it changed by minus 2 meters per second every second, right? 4 minus 2 is 2, 2 minus 2 is 0, 0 minus 2 is negative 2. Okay? So the velocity at, okay, so we got all the velocities, right? We got all the velocities. And what's g? G is negative 2 meters per second squared. So that's a crucial problem to understand. You make sure you look at that carefully and make sure you understand it, okay? All right, here's kind of a neat question for you. Okay, a cart is rolling at constant velocity. And so this is a projectile launcher. Let's pretend, right? It shoots a ball straight up. Now, when the ball comes back down, where will it land? Will it land in front of the launching tube, behind the launching tube, or directly in the tube? So pause your video and figure it out, please. Okay. Okay, so, you know, if we were sitting on this cart, we would say, yeah, the ball goes straight up. But let's say we're not sitting on the cart, we're watching it, you know? So we see this cart, you know, moving to the right. Agree? Okay, so what does that mean then? Well, it means that, okay, so what is the ball going to do? So AX is constant, right? That's what it says. I underlined it. And AY is not constant. So what did we learn about it? What's the trajectory? It's a parabola, right? Now you notice, so according to us, you know, that ball is going to have a Vy component and it's going to have a Vx component, right? Because the thing's moving when it's shot relative to us, right? Now, what is this? Okay, this thing is moving to the right with a velocity, but isn't this Vx the same as that? Of course it is, right? I mean, you know, the thing is moving to the right. So that ball is moving to the right. So when the ball gets shot, the ball has a horizontal velocity, which is the same as the velocity of the cart, right? Okay, so where's the ball going to land? Well, if the ball has the same Vx as the cart, where does the ball have to land? It has to land in the cart, you know, in the cart, all right? And again, it has to be a, you know, parabola, okay, parabola. All right, that is it. So the next time we will do some two-dimensional kinematics problems. You know, they're more work than a one-dimensional, obviously, but they're not so bad. And then we'll do relative motion, and then we'll start circular motion. Thank you very much.